next we're going to talk about how far behind one point on a wave is compared to another point on a wave. So here I've got a photograph of a wave travelling that way, and we can see that the point P on this wave is half a wave behind point Q. But we can also ask about points on two different waves. So here is another photograph of two waves travelling this way. And we can see that the dotted line wave is ahead of the solid line wave. And so the point P is on the solid line wave and the point Q is on the dotted line wave. And we can say, what's the difference between these two? And we can see that the point P is a quarter of a wave behind the point Q. Remember, the waves are travelling this way, so then as the dotted line wave moves that way, the next thing Q is going to do is move upwards. And as the solid line wave moves that way, the next thing P is going to do is move upwards to where Q is now. So P is a quarter of a wave behind the point Q on the other wave. And lastly, of course, we could also be given the displacement time graph for the point P on one wave and the displacement time graph for the point Q on a different wave, and be asked what's the difference between these 2 points, the point P and the point Q. And so if I look at this time here, for example, we can see that the difference between these 2 points on the 2 different waves is again half a wavelength. Now, if you're half a wave behind, what we do is we multiply the fraction by 2 pi, and that tells us that you're pi radians behind, and that's what we call the phase difference. Whereas how many wavelengths behind you are, that's called the path difference. So to find phase difference, first work out how far behind, how much of a wave behind one point is. Then take that fraction, multiply it by 2 pi, and that will tell you the phase difference. Now you might be thinking, why on earth can't we just talk about path difference? Why do we have to convert to phase difference? And the answer is that if this is the equation of a wave, then this is the equation of a wave that is half a wavelength behind. So the phase difference is what goes into the maths there, so that's the reason. And the last important thing to say about phase difference is to notice that for these 2 waves, it wouldn't have mattered where I had chosen to compare. Everywhere on this wave, this one is half a wave behind that one. So we say that these 2 waves have a constant phase difference, whereas these 2 waves don't. So here's the graph for the point P on one wave, and here's the graph for the point Q on a different wave, and you can see that right at the beginning there, the difference between those 2 is 0. So at t equals 0, we've got a phase difference of 0 as well. But by the time we've got to 1 second, we can see that this wave is a quarter of a wavelength ahead of that wave. And so for time equal 1 second, we can write that the path difference is a quarter of a wave, but the phase difference is pi over 2 radians. And if we keep going at each different time, we'll find that the phase difference between these 2 waves is changing all the time. So these 2 waves do not have a constant phase difference.